Los Angeles, 1963. Charles Whitman seemed like the perfect citizen, a former Marine, an architecture student, a devoted husband. His neighbors described him as polite and pleasant. But on August 1, 1966, Whitman murdered his wife and mother. Then he climbed the tower at the University of Texas, armed with a rifle and opened fire. Over the course of 90 minutes, he killed 14 people and injured 31 others before police snipers shot him dead. In his pocket, they found a note. "I don't really understand what drove me to do this. After a thorough self-examination, I've come to the conclusion that I've been a victim of many strange and irrational thoughts." He requested an autopsy on his brain. Maybe it will explain why, and it did. Doctors discovered a tumor the size of a walnut pressing against his amygdala, the part of the brain responsible for fear and aggression. The tumor had likely been growing for months, slowly warping his behavior and turning a loving man into a killer. So what does that mean? Was Charles Whitman responsible for his actions? Or was it the tumor that pulled the trigger? Here's another uncomfortable question. You've probably been in this situation. You're at the grocery store, standing in front of the fruit display, torn between buying a sugary snack or a healthy apple. It feels like your choice is entirely your own. But what if scientists could predict your decision up to 10 seconds before you consciously made it, just by watching your brain? They already have. In 1983, neuroscientist Benjamin Libet asked participants to press a button whenever they felt like it. They were also told to note the exact moment they became aware of the urge to press it. The results were shocking. Their brains showed signs of preparing for the movement 300 milliseconds before they felt the intention to act. In other words, the brain decided before they did. What we call free will might just be an after-the-fact illusion. That was 40 years ago. The debate still rages on. Some say, there you have it, proof that free will doesn't exist. Others argue, pressing a button isn't a meaningful decision. It's just a reflex. So the experiments evolved. Now researchers are studying more complex decisions. Steering in a driving simulator, choosing whether to jump off a bungee platform, even picking which charity to donate to. But the results stay eerily consistent. The brain makes the call before the mind catches up. So what are we really? Are we conscious agents with free will, or are we sophisticated biological machines running on automatic? Welcome to the most unsettling corner of science. If someone starts behind, it doesn't matter in the long run. Luck evens out over time. It's a comforting idea, and a popular one. Einstein worked as a low-paid patent clerk, almost gave up to sell insurance, and published his theory of relativity without academic backing. Andrew Carnegie was born into poverty to a weaver's family and worked 12-hour shifts in a factory for just $1 a week. He became one of the wealthiest men of the 19th century. We love these stories. We tell them in movies, books, TED Talks. But the uncomfortable truth? They're the exception, not the rule. Scientists track the lives of 50,000 children from birth to age 40. The results were brutal. If a child is born into a poor family, their chances of becoming rich are just 7%. If they're born into a wealthy family, that number jumps to 60%. And it's even worse when it comes to education. Children whose parents didn't finish school earn a university degree in only 11% of cases. But if the parents have higher education, that number is nearly 6 times higher. But this isn't just about money. Poverty literally reshapes the brain. Children from disadvantaged backgrounds have a hippocampus, the part of the brain responsible for learning and memory, that is 10% smaller. Their prefrontal cortex, which helps regulate impulses and decision-making, develops more slowly. Chronic stress doesn't just harm development, it rewires who we become. Here's the paradox. The people who were born into good neighborhoods, with good genes and good timing, often believe they earned everything through hard work and smart choices. The wealthy are twice as likely to believe poverty is the result of laziness. Top students often credit their success to their diligence, not their advantages. Psychologists call this the fundamental attribution error, the tendency to explain our own success by our character and other people's failure by their flaws. But what if we dig deeper? What if our character isn't really a choice either? Imagine two boys, born on the same day in the same hospital. The first grows up in a calm, loving home in a wealthy neighborhood with parents who read to him and feed him nutritious meals. The second grows up in a house filled with violence and addiction, in a crumbling neighborhood drinking water from lead pipes. At age 5, the first child reads books. The second watches his father hit his mother. At 15, the first is solving algebra problems. The second is dealing drugs to feed his siblings. 20 years later, the first becomes a doctor. The second ends up in prison. Society looks at them and sees a moral divide. One chose good, the other chose evil. But did either of them choose their starting point? Did the second boy choose the lead in his drinking water, which may have lowered his IQ by 10 points before he could even speak? Neuroscientist Robert Sapolsky spent 30 years studying human behavior. His conclusion is unwavering. Free will does not exist. We are the result of our genes, our environments, and random chance, none of which we choose. That idea is as radical as it is disturbing. If it's true, the entire justice system begins to unravel. Why punish people for what they were programmed to do? Why praise heroes if their greatness wasn't earned? And perhaps most unsettling of all, why do anything if everything is predetermined? I'll be honest, I avoided this question for a long time. Some ideas don't just challenge your beliefs, they shake the ground under your feet. Here's what Sapolsky himself writes in his book Determined, A Science of Life Without Free Will. This is what it means to come to the conclusion that free will does not exist. I came to this conclusion a very, very long time ago, but even I think that taking this seriously seems like utter madness. Whether or not you spend the next hour diving into that madness, well, maybe that choice was never yours to begin with. Imagine this, you're sitting in front of two buttons. You're told that thousands of lives depend on your choice, but you're not given any details. Just like in the TV series The Division. Choose, they tell you. You hesitate, then press one of the buttons. But why that one and not the other? No one's saying your molecule suddenly shifted and moved your hand like some puppet. The real question goes deeper. Why did you choose what you chose? What led to that specific decision? Earlier, I mentioned Libet's experiment and the work that followed. Neuroscientists are still debating exactly when the brain makes a decision. Some say 300 milliseconds before you're aware of it. Others say the brain starts preparing up to 10 seconds earlier. But whether it's 300 milliseconds or 10 seconds, that's not the core issue. The real question is, where does the desire itself come from? Let's zoom out. What was happening in the minutes and seconds leading up to your decision? What sensory input shaped your brain's final choice? Sometimes it's obvious. I pressed the button because someone had a gun to my head. But most of the time, it's not that clear-cut. Consider a fascinating experiment from 2011. People were placed in a room filled with an unpleasant smell. While sitting there, they were asked to fill out surveys about their attitudes toward various social groups. The results were startling. In the presence of the bad odor, participants, both liberals and conservatives, expressed more negative views toward gay men, not toward lesbians, the elderly, or African Americans, just toward gay men. A strange specificity. Let's take another experiment, but fair warning, you might want to put your tea down for this one. Participants were split into two groups. One group placed their hand in ice water, uncomfortable but tolerable. The other group submerged their hand in a liquid that looked and smelled like vomit, far more revolting. Afterwards, both groups read stories about people violating social norms and were asked to assign punishments. Some of these violations were related to cleanliness, for example, someone cleaning the toilet floor with another person's toothbrush. Others were unrelated, like someone keying a stranger's car. Here's what happened. The people who experienced physical disgust from the vomit imposed much harsher punishments, but only for violations linked to cleanliness. The cold water group, no such effect. What does this tell us? Context shapes our moral judgment far more than we think. And it's not just psychology, it's biology. Specifically, the insula, a region of the brain that lights up when mammals encounter spoiled food. That response is over 100 million years old. Tens of thousands of years ago, we humans developed something new, morality. But evolution didn't have time to build an entirely new brain structure for it. So it simply added moral disgust to the same system that processes physical disgust. To your brain, Rotting meat and rotten behavior feel oddly similar. Beauty also warps our decisions. Attractive people are seen as more trustworthy, more capable, more competent. They're elected more often, they're paid more, and they're punished less. Brain scans show that the orbitofrontal cortex, which evaluates beauty, is also active when we judge morality. Good-looking and good-hearted? To the brain, it's practically the same signal. Then there's the Macbeth effect, named after Lady Macbeth's obsession with washing her hands after murder. When people confess to unethical behavior, they often feel a need to physically clean themselves. If they lied out loud, they prefer mouthwash. If they lied in writing, they reach for hand sanitizer. It's as if the brain believes a lie actually dirtied the body. Even physical comfort affects our moral choices. Hungry judges are less likely to grant parole. In one experiment, participants given ginger, which soothes the stomach, were more forgiving when judging violations involving filth or impurity. Let's return to our experiment, the one where you have to make a choice and press a button. Let's slow it down and really think about it. What's happening in the minutes, hours, even days leading up to that decision? For starters, your bloodstream is constantly circulating hormones. Take testosterone, for example. Despite the popular myth, testosterone doesn't directly cause aggression, but when levels are elevated, people become more confident in games, less cooperative, more prone to risk-taking, and less empathetic. Even neutral facial expressions start to seem more hostile. Testosterone levels can fluctuate depending on the time of day, recent illness, physical injury, arguments, or sex. And that's not the whole picture. The brain's sensitivity to testosterone varies wildly between individuals. Some people have 10 times more testosterone receptors than others. Why? It depends on genetics, prenatal development, and environmental factors. Other major player is oxytocin, often called the love hormone. It plays a key role in social bonding, especially between a mother and child. Under its influence, people become calmer, more generous, and more trusting. But there's a catch. Oxytocin doesn't make us universally kind, it makes us kinder to our own. In a study conducted in the Netherlands, participants were given oxytocin and then asked to make moral decisions involving hypothetical lives. They were more likely to sacrifice someone with a German or Middle Eastern name than someone with a Dutch name. Oxytocin boosted empathy, but only within the in-group. At the same time, it increased aggression and prejudice toward outsiders. Stress hormones also shape our choices. When you're under pressure, these chemicals flood your system, raising your blood pressure and heart rate, pulling energy from reserves and even suppressing reproductive function. In the brain, they activate the amygdala, increasing fear and reactivity, and suppress the prefrontal cortex, the area responsible for thoughtful judgment and empathy. The result? More impulsive decisions and less concern for others. So far, I've only mentioned 3 classes of hormones, but the human body produces around 75 different hormones, and each of them quietly, constantly, invisibly influences your brain and behavior. Some act in minutes, others in mere seconds. But the real, lasting changes take place over days, weeks, and years. That process is called neuroplasticity, the brain's ability to physically reshape itself in response to experience. And yes, there's a whole video about that too. You won't want to miss it. Long-term experience doesn't just change your perspective, it physically reshapes your brain. Synaptic excitability increases, new neural connections form, dendrites grow. Some neurons die and new ones are born. Entire brain regions can expand or shrink to the point that it's visible on a brain scan. Post-traumatic stress, for example, enlarges the amygdala, increases the number of synapses, and lowers the threshold for fear and aggression. Depression shrinks the hippocampus, impairing memory and learning. On the flip side, regular physical activity or growing up in a stimulating environment actually increases hippocampal volume. But experience doesn't stop at the brain. Chronic stress causes the adrenal glands to flood your body with glucocorticoids. New fathers experience a drop in testosterone, and the more attention they give their newborns, the more their testosterone falls. Even your gut bacteria influence behavior. In fact, there are more bacteria in your digestive system than cells in your body. They affect appetite, anxiety levels, and even gene expression in neurons. Now, You might be thinking, sure, but I'm an adult. I can take control of this. Get some lab work done, eat salad instead of chips, go for a run, subscribe to a channel, and feed your brain new knowledge. Great. Let's say you're right, but first, let's rewind a bit. You're a teenager. Your brain is almost fully developed. Almost. One major area, the prefrontal cortex, still has a decade to go. This is the part of the brain responsible for planning, emotional regulation, impulse control, and decision-making. Teenagers actually have more synapses in this region than adults. Over time, unnecessary connections are pruned, and the structure becomes more efficient. This delay explains a lot of classic teenage behavior, mood swings, impulsive choices, poor planning. But more importantly, it means that during adolescence, the brain's most sophisticated region is undergoing massive construction. And what's it built from? Your teenage experiences. What happens during this window plays an outsized role in shaping how you'll make decisions for the rest of your life. So why does the prefrontal cortex take so long to mature? In other primates, it finishes developing around puberty, but humans need an extra 10 years, not because our cortex is more complex. It isn't, structurally. It's because our social rules are. Think about what a teenager has to learn. When it's okay to lie for the greater good, and when it's not. How to behave differently with parents, friends, teachers, strangers. Which rules are flexible and which are not. When to hold back emotion and when to let it out. You can't encode all that in DNA. The variety of human cultures is too vast. It has to be learned through experience. And so, evolution made a trade-off. Slow down the development of the prefrontal cortex and let the environment do the teaching. It's as if nature said, this part of the brain, let experience, not genes, shape it. Now, let's rewind even further to early childhood. This is the era of full-scale neural construction. Logical thinking, emotional control, memory, cognitive ability, everything is being wired up. And that wiring is shaped by countless factors. Parenting style, peer interactions, neighborhood safety, access to books and healthy food, and, ultimately, culture. There's even a scale for this, the Adverse Childhood Experiences score. Each additional negative experience, abuse, neglect, instability, increases the risk of antisocial behavior in adulthood by 35%. And even something as random as your birth month can shape your trajectory. No, not astrology, real data. Children who are slightly older than their classmates are usually more cognitively advanced. Teachers give them more attention, more praise, and those early advantages accumulate over time. All of this helps shape the adult brain. But of course, these are trends, not destiny. Many people defy predictions based on childhood conditions. Still, the big picture remains. We don't choose the family we're born into, and long before we take our first breath, the environment starts shaping us. Everything circulating in the mother's blood enters the fetus. Hormones, immune factors, inflammation markers, toxins, medications. Excess maternal stress raises glucocorticoids, increasing the baby's future risk of anxiety and depression. Elevated prenatal androgens raise the likelihood of aggression and poor emotional regulation. Maternal malnutrition raises the risk of schizophrenia and metabolic disorders later in life. In short, prenatal experience matters. And it's a lottery. And if you didn't choose your womb, you certainly didn't choose your genes. Yet genes, too, influence decisions in ways more surprising than you might think. Genes encode proteins, the fundamental building blocks of your body. Proteins create different types of cells, construct neurotransmitters and hormones, and make up enzymes and receptors. Each of your roughly 20,000 genes codes for a specific protein. But genes don't decide anything. Saying a gene chooses when to activate is like saying a cake recipe decides when to be baked. Genes are switched on and off by the environment. And here's something even more surprising. Only about 5% of your DNA consists of actual genes. The remaining 95% is a complex regulatory system of switches, turning genes on or off depending on countless factors. In fact, most evolutionary changes happen not because the genes themselves change, but because their regulation does. People differ in the variants of genes that influence behavior. Variants of serotonin genes are associated with mood, arousal, and impulsivity. Dopamine gene variants affect motivation, reward, planning, addiction, and attention. But even the same gene variant can function very differently depending on context. For example, a certain version of a serotonin-processing gene is linked to increased antisocial behavior, but only in people who experienced abuse as children. A dopamine receptor variant is associated with poor impulse control, but only in conditions of poverty. There are about 16,000 genes actively working in the human brain. Each one can vary at around 250 points. That's 4 million places where your genetics might differ from someone else's. 4 million opportunities for the genes you didn't choose to interact with the childhood you didn't choose either. This is the genetic lottery, and it plays a massive role in shaping your vulnerabilities and potential. And that's only half the story. Culture molds our desires, values, and decisions more deeply than we tend to realize. Every culture has mechanisms to shape individuals into replicas of their ancestors, to ensure continuity. Just look at the difference between individualistic and collectivist societies. In the United States, the emphasis is on autonomy, personal achievement, and individual rights. In East Asia, values like harmony, interdependence, and social cohesion take precedence. These differences run deep. Americans use the word "I" more frequently and define themselves by their careers. I'm a lawyer. East Asians often define themselves relationally. I'm a daughter. I'm part of this family. Their memories differ too. Americans focus on personal events. The summer I learned to swim, while East Asians remember relationships. The summer we became friends. Even children's drawings reflect this divide. American kids place themselves at the center of their family portraits. Asian kids draw themselves off to the side as part of a group. The American goal is to stand out. The East Asian goal is to fit in. Neuroscience backs this up. In Asian brains, the dopamine reward system lights up in response to calm faces. In American brains, it responds more to excited expressions. When shown complex scenes, East Asians memorize the whole image almost instantly, while Americans zero in on the central figure. Stress reactions also differ. Americans feel stress when asked how others have influenced them. East Asians feel stress when asked how they've influenced others. Where do these differences come from? American individualism is rooted in immigration, a process that's selected for people willing to leave everything behind to start anew. East Asian collectivism, meanwhile, is tied to the ecology of rice farming. Growing rice requires massive group coordination, building terraces, digging irrigation channels, harvesting together. In northern China, where wheat, which can be grown individually, replaces rice, people are more individualistic, much like Westerners. Even religion follows this pattern. Harsh, dry climates like deserts tend to produce monotheistic religions, with strict rules and judgmental gods. Lush, abundant environments like rainforests tend to give rise to polytheistic systems, with many gods and a more relaxed moral framework. The monotheisms of the desert proved more successful at conquest, which is why more than half the world now follows religions born among Middle Eastern shepherds. Occupations shape culture too. Cattle herders whose wealth is mobile and easy to steal historically developed cultures of honor, marked by extreme hospitality, rigid codes of conduct, and violent retaliation for insults. Even the strictness of a society's cultural norms can be predicted by history. Countries that have faced epidemics, invasions, or natural disasters often develop tighter norms. Amazingly, a study of 33 countries found that the population density 500 years ago is a strong predictor of how strict a society's norms are today. How can events from 5 centuries ago shape modern behavior? Through generations. Culture passes through parenting, rituals, songs, and stories about vengeance or forgiveness, about punishment or empathy. And yet, even under strong cultural pressure, individual variation remains enormous. Every society produces outliers, like Nelson Mandela, who chose peace over revenge after 27 years of imprisonment. Culture sets the trends. It doesn't set your fate. So what does make us who we are? Robert Sapolsky's answer is stark. We are defined by everything that came before: the smell in the room, the hormones in your blood, the events of your prenatal life, your parents' trauma, your society's values, your ancestors' migration patterns in the 1500s. All of it flows into you. You chose none of it. And in this unbroken stream of influences, there's no room for the traditional idea of free will. As legal scholar Pete Alsays put it, there is no longer a gap between nature and nurture that moral responsibility can fill. This continuous flow explains why misfortune tends to multiply. Imagine a person with a gene variant that makes them more sensitive to stress. That person suffers more under the same conditions in childhood. Those early struggles lead to a more limited environment in adulthood. Then, when a rare opportunity appears, their sensitivity prevents them from recognizing it or believing they deserve it. To prove free will exists, you'd need to find a neuron untouched by the other 80 billion neurons around it. A neuron that functions outside the influence of hormones, prenatal conditions, gut microbiota, and the millions of genetic variants that make up your brain. Science hasn't found one and likely never will. Why does an event happen? Because something happened before. And why did that happen? Because something else happened before that, and so on ad infinitum. But this is not absurd. This is how the universe works. It is absurd to close our eyes to this inseparability, to think that we have free will and that it exists because at some point the state of the world, or the frontal cortex, or a neuron, or a serotonin molecule, that preceded behavior arose out of nowhere. The universe operates according to rules. Every cause has an effect. Every biological state is caused by a previous one. For decades, scientists believed that if you break a complex system down into its individual parts and understand each one, you can understand the whole. It's like an old laptop that won't turn on. A skilled technician opens the case, checks the hard drive, the memory, the cooling system, the motherboard. He finds a burned-out capacitor, replaces it, and the machine comes back to life. Problem solved by reducing the system to its components. But what if that's not always true? What if some things can't be understood by taking them apart? What if certain outcomes aren't determined by what came before? What if reductionism fails? This idea upended our entire view of the universe in the 20th century. Einstein's theory of relativity, Heisenberg's uncertainty principle, theories of chaos, emergence, and quantum randomness. It was a full-blown revolution in science. In the 1960s, meteorologist Edward Lorenz at MIT was building a computer model to simulate weather using 12 variables like temperature, humidity, and pressure. One day, he paused the program to grab lunch. When he returned, he restarted the model, but instead of starting from scratch, he typed in the values printed on his readout and resumed from where he left off. What he saw stunned him. The new simulation quickly veered off course. With each iteration, it drifted further from the original. Eventually, the two forecasts looked nothing alike. Lorenz searched for an error and discovered that the only difference was that the printed data had been rounded slightly. That tiny deviation completely changed the future of the system. This was the birth of chaos theory. In 1972, Lorenz famously described this phenomenon as the butterfly effect. The idea that the flap of a butterfly's wings in Brazil could cause a tornado in Texas. In linear systems, small changes lead to small consequences, but most of the universe is non-linear, meaning interactions multiply in unpredictable ways. Imagine a universe with only the Earth and the Moon. Easy enough to model, but add the Sun and suddenly it's chaos. The Moon affects the Earth, which affects how the Earth affects the Sun, which loops back and influences the Moon again. This is the famous three-buddy problem, a seemingly simple system whose future is inherently unpredictable. To experiment with chaos right now, all you need is a piece of graph paper or just watch the screen. Each square on the grid can be empty or filled, a simple 0 or 1. We start with one row of randomly filled cells. Then we apply a rule to generate the next row. Let's begin with a simple one. If the cell above is filled, the one below is filled. If the cell above is empty, the one below is empty. You'll do that row after row, and you get boring vertical stripes, predictable. Now let's flip the rule. If the top cell is filled, the bottom cell is empty. Still predictable. Okay, let's make it slightly more complex. Now, each cell in the new row depends on 3 cells above it, the one directly above and its 2 neighbors. Here's the rule. Color the cell only if exactly one of those 3 cells is filled. We start with a single filled square in the top row. Apply the rule again and again. At first, nothing strange, just a triangle. But keep going. After a few dozen rows, a pattern emerges, the Sierpinski triangle, a self-repeating shape found all over nature. What you're seeing is called a cellular automaton, a simple system that evolves over time by applying fixed rules. This particular rule is known as Rule 22. There are 256 possible rules for one-dimensional automata like this. Most produce boring results, repetitive, fading, or symmetrical, but a rare few, produce dazzling complexity. Try changing the starting row. Some initial configurations explode into intricate designs, others quickly die out. Some freeze into static patterns. Sound familiar? It should. Biology does the same thing. We see these patterns on mollusk shells, in animal skin, in plant leaves. On the left, a real shell. On the right, a pattern generated by a cellular automaton, almost indistinguishable. Life, it turns out, is full of these mathematical echoes. Rule 22 is one of the most famous cellular automaton rules. Entire academic careers have been built around studying it. But what makes Rule 22 so special? Depending on its initial state, it can generate three types of behavior. The first, extinction. The pattern quickly vanishes, leaving behind a void. The second, crystallization. The system freezes into a regular, predictable pattern. The third, something resembling life. The pattern grows, branches, mutates. Structured regions give way to chaotic ones. Chaos gives way to order, then back again. And here's the astonishing part. It's impossible to predict which outcome a particular initial state will produce. Want to know what the 100th or 1000th row will look like? There's only one way. Simulate every step, one by one. You can't break the rule into parts or shortcuts and predict the outcome. Many brilliant mathematicians have tried. All have failed. Even when a pattern appears chaotic, there's no guarantee it won't settle into a boring repetition after a million generations. For example, take this initial row. It fades by the third iteration. Now, change just one cell, fill in one more square, and suddenly the pattern explodes into a persistent structure. A biologist would say, one cell mutated and triggered a cascade. A mathematician would say, the system is sensitive to initial conditions. A poet might say, a butterfly flapped its wings and changed everything. Cellular automata are fascinating not just for their beauty but for their power. They can model biological systems, an idea popularized by physicist and computer scientist Stephen Wolfram. And they don't have to stay one-dimensional. There are two-dimensional, three-dimensional, even more exotic versions. The most famous of all is Conway's Game of Life, invented by mathematician John Conway. It takes place on a two-dimensional grid. Cells live or die based on a few simple rules. That's it. Yet from those rules emerges extraordinary complexity. There are self-replicating structures, patterns that move like intelligent agents, gliders, oscillators, replicators. With enough complexity, you can even build logic gates and entire computers using just Game of Life rules. If you want to try Conway's Game of Life yourself, the link is in the description. Chaos theory has overturned our understanding of predictability. It showed that even in deterministic systems, behavior can be wildly unpredictable. It revealed that simple rules can give rise to staggering complexity. And that insight changed everything, not just in mathematics and physics, but in biology, economics, psychology, and even philosophy. And most intriguingly, it breathed new life into the ancient debate about free will. If a system governed by strict rules can behave in ways no one can foresee, if its future cannot be compressed into a neat equation, then maybe, just maybe, our freedom hides there. When Edward Lorenz published his revolutionary paper in 1963, it was met with silence. The idea that the world might be fundamentally unpredictable didn't sit well with traditional science. Years passed before anyone took notice. His first allies were graduate students, young physicists curious about strange systems. Legend says some of them studied chaos through the behavior of dripping faucets and psychedelic experiences. The scientific establishment ignored them. Part of the problem was the name. Chaos theory sounded like a bad sci-fi novel, but the bigger problem was deeper. Science had grown used to reducing systems to manageable variables, creating the illusion of order. Non-linear chaos, with its swirling feedback loops and sensitivity to conditions, seemed like a nuisance, an outlier best ignored, until it became clear chaos is at the heart of life itself. Biological cells, nervous systems, societies, they're not clocks to be taken apart. They're chaotic systems, more like weather, less like watches. By the 1980s, chaos theory was booming. Those curious graduate students were now professors at Oxford. Some launched companies to apply chaos theory to the stock market. Conferences, journals, and interdisciplinary centers appeared. Chaos was studied in education, governance, markets, art, and architecture. One proposal claimed we find nature more beautiful than modern buildings because nature contains just the right amount of chaos, an aesthetic sweet spot between structure and randomness. There were even theological essays linking chaos to spirituality. One was titled, "Chaos as the Union of Heaven and Hell." The author wrote, "Those of us who wish to combine modern culture with theological thought cannot afford to ignore chaos theory." Some began to argue that the unpredictability of human behavior is exactly the place where free will lives. After all, at every fork in the road, we make decisions. Sometimes they change everything. And no one, no scientist, no equation can predict them. Physicist Gert Eilenberger put it this way: mathematical models can never fully capture reality. The mathematical abilities of Homo sapiens are biologically limited. Because of chaos, Laplace's determinism cannot be absolute, and the question of freedom is once again open. Biophysicist Kelly Clancy shares a compelling view. Since chaos can be controlled, it provides a balance between stability and exploration. And since it is unpredictable, it is a serious candidate for the dynamic substrate of free will. And Doing Farmer, one of the early pioneers of chaos theory, echoes this idea. Philosophically, I was struck by the fact that chaos is an effective way of reconciling free will with determinism. The system is deterministic, but we don't know how it will behave. Sounds like a perfect solution. We live in a deterministic universe, but because it's unpredictable, we're still free, right? Well, not quite. There's a catch, and it's a fundamental one. It lies in confusing determinism with predictability. Here's the distinction. Determinism means everything has a cause. Events unfold according to laws. Predictability means we can foresee what's going to happen. These are not the same. Let's take a simple example. Imagine a giant sheet of paper and the initial state of a cellular automaton. You spend a year applying Rule 22 row by row. In the end, you get a complex but precise pattern. Now redo the entire process. Same initial row, same rule. The result will be identical. Let a trained dolphin do it. Same outcome. Why? Because the system is deterministic. It must unfold exactly the same way every time. Now, let's switch to real life. The year is 1922. We observe 5 young boys. Fast forward 40 years and one of them becomes violent. He robs and attacks people. Can we predict which one? No. It seems random. And when it happens, we say, he chose to do it. He's just a bad person. Now it's 2025. Same scenario. 5 young people. But now we have access to genetic data. One of them carries a damaged MAP gene, which affects tau protein production in the brain. We now know, by the age of 60, this person has a much higher chance of developing frontotemporal dementia, a condition that often includes aggression. When it finally happens, we don't say, he's a bad person. We say, he has a broken gene. He's a sick person. What changed? Not the behavior, but the explanation. From this perspective, free will is just biology we haven't figured out yet. Once we understand the cause, the freedom disappears. Chaos is fascinating because it shows how simple rules can give rise to complex and unpredictable outcomes. But there's a deeper problem lurking underneath. Imagine a real-world scenario. 3 houses stand side by side on the same street. In the house on the left, the owner neglects faulty wiring. A fire breaks out. In the house on the right, same story. A fire starts. Both fires spread inward and burn down the house in the middle. The owner of the middle house sues both neighbors, but each neighbor says the same thing. Even if my house hadn't burned, the other one would have destroyed yours anyway. Before 1927, courts accepted this argument. No one was held liable. Then everything changed. The court decided that the blame could be shared equally. Imagine a group of soldiers lined up in a firing squad to carry out a death sentence. No matter how vigorously a soldier pulls the trigger in obedience to God and country, he is sometimes weighed down by a certain ambivalent feeling, perhaps a feeling of guilt for killing a human being. Centuries of such practice led to cognitive manipulation. One of the soldiers was given a weapon loaded with blank cartridges. No one knew who got it, so everyone thought it was in their hands, and therefore, in reality, they were not murderers. When lethal injection devices were invented, in some states, their design included 2 different syringes containing poison. 2 people press their buttons, and an automatic randomizer injects the poison from one syringe into the condemned person's vein, while the contents of the other are poured out. How the syringes and buttons are connected is not recorded anywhere. Thus, each participant in the execution knows that the other could have been the executioner. Nice psychological tricks that blur responsibility. So, chaos theory plays a clever psychological trick. It makes behavior seem unexplainable, as if the complexity itself is a sign of freedom. But that's an illusion. Just because we can't precisely trace the cause of a complex behavior doesn't mean there is no cause. If we don't know which neighbor's negligence started the fire, that doesn't mean the house spontaneously combusted. If we can't identify which soldier pulled the trigger, that doesn't mean the condemned man died of old age. The same applies to human behavior. Just because we can't trace all the causes back to the very beginning doesn't mean they don't exist. Chaos still obeys rules. Every step follows rigorously from the one before. The system is completely deterministic. We simply cannot predict the future without simulating every step along the way. Yes, free will sounds more poetic than we don't understand it yet, but the truth is simpler and harsher. Chaos is deterministic, it's just unpredictable. Almost everyone agrees on one point. Free will does not live in a single neuron. A neuron is just a biological machine. It cannot violate physics. But what if we combine many neurons? Philosopher Christian List argues that we're looking for free will at the wrong level. It cannot be found at the physical level. Neuroscientist Robert Kane adds, we don't need to manually control every neuron. These thinkers believe that free will is an emergent property, a phenomenon that arises when simple components form a complex whole. Let's take that seriously, but then we must ask, how exactly does the simple become complex? Imagine a single ant wandering aimlessly along a branch. Now 10 ants, still chaos. Now 100 ants, and something begins to shift. 1,000 ants, and now we have a colony. A self-organizing system emerges. They divide labor. They build bridges and rafts using their own bodies. They dig underground nests with water-resistant tunnels. They set up specialized chambers, one for mushrooms, one for eggs, one for storage. No one ant has a blueprint. No one gives orders, yet the system behaves intelligently. What's the recipe for this emergence? A large number of simple agents. Each follows a limited set of rules, random interactions filtered through those rules, feedback loops that reinforce certain behaviors. For example, carry a pebble until you meet another ant carrying a pebble, then drop yours. No ant knows what it's building, but the colony knows. This is emergence. New properties arise at the group level that do not exist at the individual level. A single water molecule isn't wet. Wetness is an emergent property. A single neuron doesn't have thoughts. A brain does. These emergent patterns can be stable. Like a waterfall, its shape stays the same, even though no water molecule passes through twice. Another striking example, honeybee swarm intelligence. 2 scout bees find different food sources. They return to the hive and dance. Literally, the better the source, the longer the dance. Other bees wander randomly. When they bump into a dancer, they follow the dance, go out, check the food, and return to dance again. The better the food, the more bees dance for it. Soon, the best source dominates. No bee makes a central decision, but the colony chooses optimally. This is swarm intelligence. Or take the case of slime molds, those weird creatures that can't decide whether they're fungi or amoebas. Just kidding. They confuse biologists for good reason. Technically, a slime mold is a massive, single-celled organism with many nuclei. It spreads out over surfaces looking for food. Now, place it in a dish with two corridors, one leading to a single oat flake, the other to two flakes. The slime mold explores both paths, but eventually abandons the lesser one and settles on the more rewarding option. If one path is shorter, it chooses that too. It can even solve mazes with multiple dead ends, choosing the most efficient route. Japanese biophysicist Atsushi Taro conducted an astonishing experiment. He placed a slime mold on a nutrient-rich surface, shaped like the Tokyo metropolitan area. Oat flakes represented the suburban railway stations. The slime mold began at the location corresponding to central Tokyo, and over time it grew a web of threads that mirrored the actual Tokyo rail system. Slime mold. 0 neurons. Engineers. Decades of planning. Final score. 1 to 1. What does this tell us? Simple systems can produce remarkably efficient outcomes, even without centralized control. And the same logic applies inside the human brain. In early brain development, a growing neuron sends out two branching scout fibers, each seeking a target. Target neurons release chemical attractants. One releases slightly more, better, match. The scout fiber moves toward that one, strengthening the connection. The result is a branching neural tree. But here's the twist. There's no master plan. The genome doesn't contain step-by-step instructions for every one of the brain's 100 trillion synapses. That would be impossible. There aren't enough genes. Instead, biology uses simple, recursive rules, just like in trees. Step 1. Start with a tube of a certain diameter. Step 2. Lengthen it until it is 4 times longer than the diameter. Step 3. Split and repeat. That's it. This tiny genetic recipe builds neurons, blood vessels, bronchi, and forests. But self-organization is only part of the story. There is another pattern in nature that unites ants, neurons, and human communities. 80% of interactions occur with 20% of participants. 80% of complaints come from 20% of customers. 80% of the work is done by 20% of employees. When food is scarce, animals search for food within 20% of their previous range. This optimizes energy expenditure. Dolphins communicate in an 80-20 ratio within families and between families. This stabilizes groups, but allows for the exchange of information. Here's another example of an incredible pattern. Scientists have learned to grow three-dimensional cultures of neurons. Thousands of cells float in a nutrient solution, find each other, and connect. After a few months, these microscopic clusters self-organize into brain structures. The neurons of the cortex form a primitive cortex with layers and hints of cerebrospinal fluid. Over time, the organelles begin to produce synchronized brain waves. A random handful of neurons spontaneously self-organizes into the beginnings of a human brain. What does this mean? Biological systems generate complexity and optimization that rival the achievements of engineers and mathematicians. These systems arise from simple interactions between simple parts, without centralized authority, without a planner. They have properties that exist only at the system level. Their behavior can be predicted without knowing the details of the components. Our brain uses the same tricks as slime molds and ants, and there is no magic involved. All of this is true for our deterministic world, no matter how chaotic it may be. Except, what if the world itself is not deterministic at all? You've probably looked at dust particles in a sunbeam at least once. For example, sitting in a dark room when light shines through the window. These tiny particles in the air do not float calmly. They rush and jump as if they were alive. This is an example of uncertainty right before your eyes. This phenomenon was first noticed by Robert Brown in 1827. Later, scientists understood what was happening. The particles collide with air molecules, which themselves are in chaotic motion. These collisions give the dust particles random jolts, and everything begins to move randomly and unpredictably. This is not the unpredictability of a cellular automaton, where each step is deterministic. Here, the state of a particle does not depend on the previous moment. Laplace is turning in his grave. Brownian motion is important for biology. Thanks to it, molecules inside cells are constantly moving and colliding with each other. When a fertilized egg divides, some of the molecules are distributed randomly, and it is Brownian motion that is responsible for this. As a result, the two newborn cells already have different abilities to produce energy and regulate genes. With each division, chance amplifies the differences between the cells that ultimately make up you. Scientists did not stop at particles. They looked even deeper, into the subatomic world, and they were horrified by what they saw. It all began with Thomas Young's experiment in 1801. He directed a beam of light at a barrier with two slits behind which was a screen. The light passed through the slits like a wave. If we replace the photons of light with electrons, we get the same wave pattern. If we send just one electron through the slits, nothing changes, the same wave. A single particle passes through both slits at the same time. That is, it is in two places at once. But the strangeness is just beginning. Let's place a detector at the slits to record the passage of the electron. Now each electron passes through only one slit, at random. The measurement process causes the electrons to cease exhibiting wave properties. The wave function collapses, and the electron begins to behave like a classical particle. It seems as if the electron senses the observation. This is related to Heisenberg's uncertainty principle. While the electron is in a wave state, it has no definite location. It exists in a superposition of possible states. After measurement, its coordinates can be determined precisely, but information about other characteristics, such as momentum, becomes less certain. Any measurement inevitably affects the system. The next oddity is quantum entanglement. Quantum entanglement, two particles can become entangled. This means that their quantum states are interconnected. If, during measurement, one electron has an upspin, then the particle connected to it will necessarily show a downspin. Entangled particles can be located at a great distance from each other. The current record is 1,200 kilometers, but in theory, there is no limit to this distance. And here's the strangest thing: when one particle is measured, the state of the other is determined instantly, faster than the speed of light. An electron in a distant nebula can be entangled with a particle of a cucumber shriveled in the far corner of your refrigerator. The subatomic world is fundamentally indeterministic. Particles are in several places at once. Measurements of entangled particles correlate instantaneously over vast distances. Particles even penetrate solid objects. If there is room for such a thing in the universe, can we confidently deny free will? Perhaps it too is hidden in this strange quantum world. When news of quantum mechanics and its oddities appeared in science, specialists in many disciplines went into a tailspin. Quantum psychology, quantum spirituality, quantum activism, and even, God forgive me, quantum cancer healing appeared. Ridiculous? Perhaps. But among those fascinated by such theories was Nobel laureate John Eccles, one of the greatest neuroscientists. He suggested that the mind emits psychons that control dendrons in the brain through quantum tunneling. Eccles did not simply reject materialism. He introduced the category of the soul, which supposedly freed the brain from some of the laws of physics. But the ideas of quantum free will encountered three serious obstacles. The first was the problem of scale. Quantum effects exist at the level of electrons. Can they influence molecules, neurons, and moral beliefs? Almost all experts say no. Quantum effects are blurred and cancel each other out in the warm and humid brain. Some try to prove the opposite. There is a theory that the uncertainty of the position of a magnesium atom in a receptor can grow to the level of entire neurons. Hamerhoff and Penrose focused on microtubules in neurons, assuming quantum entanglement between them. But here are the numbers. There are about 200 receptors in one synapse. A neuron has 10 to 50,000 synapses. There are 10 million neurons in the hippocampus. That's 2,100 trillion receptors. How likely is it that quantum events would occur simultaneously in enough receptors to have a real effect? Synapses can indeed behave randomly. Nobel laureate Bernard Katz showed that a neurotransmitter can be released spontaneously. But this is not quantum magic. Spontaneous release has its own mechanical causes. It is regulated by external factors and serves a useful purpose. A synapse conditionally warms up after inactivity, like a car engine. The second problem is even more important. If quantum uncertainty influenced our behavior, it would be simply random. As philosopher John Searle writes, the hypothesis that some actions are performed freely is not at all the same as the hypothesis that they are performed randomly. Sam Harris adds, if quantum mechanics is related to free will, then every thought can be explained by the phrase, "I don't know what came over me." You wouldn't even be able to speak. The muscles of your speech apparatus would contract randomly. Opponents of quantum free will have tried to get around this. For example, they proposed the idea of filtering. Randomness is generated, but our eye sets a filter. That is, you consciously choose between random options. But in such a model, the first ideas for saving a drowning child could well be, do a somersault, go check your tax debt, squeak like a dolphin. The main problem, where does a filter with your values and criteria come from? You literally have to descend to the quantum level and intervene in the process. Tell us in the comments if you know how to use the power of thought to interfere with the work of your electrons. But so far, science knows of no such cases. The revolutions of chaos and quantum uncertainty have highlighted the limitations of reductionism. The most interesting things about people cannot simply be taken apart and explained. But anti-reductionism still does not give rise to free will. It does not mean that the constituent parts work differently when there are many of them, or that complex things arise on their own. So what does that mean? We are the sum of everything that is beyond our control. Biology, the environment, and their interaction. We simply cannot not want what we want. But why get out of bed at all if we are machines with automatic decisions? Scientists decided to test a frightening hypothesis. What if people really believe in the absence of free will? Won't they start doing crazy things? The experiment was simple. The researchers gave people an excerpt from a book by Francis Crick, the man who discovered the structure of DNA. In his old age, Crick became fascinated with the brain and wrote rather harshly, "You are nothing more than a bunch of neurons." The control group read a neutral text. At first, the results looked depressing. People who wavered in their belief in free will began to cheat more often, took more money from the common fund, and helped strangers less. They even took revenge more fiercely, literally. When they were allowed to measure out the amount of hot sauce for their offender, they doubled the portion. But then the nuances emerged. First, the effect was tiny. No one turned into a maniac. At most, they became slightly less decent. Second, reading one excerpt from the Scream is not enough to truly destroy one's belief in free will. This belief is formed over years, starting in childhood. Most importantly, when other scientists tried to repeat the experiments, many failed. If free will doesn't exist, how can anything change? The answer lies in a sea slug called aplysia. It learns reflexively, biologically, without choosing. Shocks lead to gene activation and stronger neural connections. Mammals work the same way, even humans. A sticker that says, "Be kind," can make you act more generously. Trauma, hormones, and experiences reshape your brain. We don't choose to change, we're changed. So what do we lose by letting go of free will? Not morality. Studies show people behave just as ethically, even without belief in free will or divine punishment. The fear is existential. If we don't choose meaning, does life have any? But maybe letting go brings compassion. Obesity isn't laziness, it's biology. So are bipolar disorder, ADHD, autism. Yet people still blame themselves for what they didn't choose. In the end, neuroscience points to one truth. You don't deserve happiness more than anyone else, but no one deserves it less than you.